In this video, we are going to study about the packing efficiency. Now, what do you mean by packing efficiency? We know that in a crystal lattice, there will be voids or empty spaces present. Now, packing efficiency means it is the percentage of total space filled by the particles. So, we are going to calculate the packing efficiency in HCP and CCP or FCC, then packing efficiency in BCC and packing efficiency of a simple cubic lattice, and we are going to compare which has more packing efficiency. So, the meaning of the word packing efficiency is it is the percentage of total space filled by the particles. Now, let's first derive and find out the percentage packing efficiency in HCP, that is hexagonal close packing, and CCP or FCC. So, first we are going to find packing efficiency in HCP and CCP or FCC structures. We know that HCP, hexagonal close packing, CCP and FCC both are same, cubic close packing or face centered cubic close packing. Now, for this we have to draw a diagram. That is, I am going to draw a cubic close packing. Now, this is A, B, C, D, E, F, G and H. Now, we have the edge length AB as equal to A. So, this is edge length A, and BC, all the edges are of same length, BC also as A, and you know that this is a packing efficiency in face centered cubic lattice. What is the meaning of face centered cubic lattice? We have atoms at the corners, 8 corners, and the center of each face. So, we are going to consider only one face here to derive the packing efficiency. So, we have AB is equal to BC. AB is equal to BC is equal to A, that is our edge length, and we have AC. So, here we have an atom, here face and this corner also. So, this is AC. AC is the face diagonal. AC. Let this AC be equal to B, which is the face diagonal. And we know in FCC the spheres touch each other along the face diagonal. So, this is equal to B. This is B. Now, this sphere is 2R, and this is R, and this is R. So, what will be B? B will be equal to 4R. So, this is the diagram of a cubic close packing. Now, let us see the derivation. That is, we are going to calculate the packing efficiency. Now, we know that in FCC or CCP, what is the number of atoms present? Number of atoms is equal to 4. So, let us write that first. In FCC, number of spheres, here we consider the atoms as spheres, is equal to 4, and the expression for packing efficiency percentage is equal to volume occupied by 4 spheres. Why 4 spheres here? Because the number of atoms or spheres present in FCC or CCP is equal to 4. So, volume occupied by 4 spheres divided by total volume of unit cell Now, let R be the radius of the sphere, and we know volume occupied by one sphere is equal to 4 by 3 pi r cube, where r is the radius of the sphere. So here we have 4 spheres. So volume occupied by 4 spheres will be equal to 4 into 4 by 3 pi r cube. Now, we know that in FCC the atoms or the spheres touch each other along the phase diagonal. So, you can write from this the phase diagonal. The phase diagonal in the figure is AC. Phase diagonal AC. Phase diagonal AC is equal to B, and B is equal to 4R. Now let's consider triangle ABC. So in triangle ABC, we can write AC square is equal to AB square plus BC square. And what is AC? AC is B. So B square is equal to AB and BC. They are the edges. So A square plus A square, or B square is equal to 2A square, or we can write B is equal to root 2A. Now we know that B is equal to 4R. So substitute that in this. B is equal to root 2A. We get root 2A is equal to 4R, or we can write A is equal to 4 by root 2R. Now I am going to write this A as A is equal to 4 into root 2 divided by root 2 into root 2R. Now root 2 into root 2 is 2. 4 by 2, 2, or we can write A, edge length A is equal to 2 root 2R. Now study this expression for edge length A of FCC or CCP and HCP. What is the expression to find the edge length in FCC? It is A is equal to 2 root 2R, where A is the edge length and R is the radius of the sphere. Now we got the expression for A, or from this you can write the expression for R also. What is the expression for R from this? R will be equal to A by 2 root 2. So learn both the expressions, very important. Now you know that the volume of the cube. So the expression for packing efficiency is volume occupied by 4 spheres divided by total volume, and volume of the cube is equal to A cube. So we are going to write volume of cube is equal to A cube, and we got A as 2 root 2R. Therefore, we can substitute that as A cube, which is equal to 2 root 2R the whole cube, which is equal to 16 root 2R cube. Now we can substitute in the expression for packing efficiency. Therefore, packing efficiency is equal to volume occupied by 4 spheres is 4 into 4 by 3 pi r cube divided by 16 root 2 r cube. When you solve this, you get the percentage as 74%. So what can you say from this value, 74%? 74% of the space is filled by particles in case of hexagonal close packing and cubic close packing or face-centered cubic close packing structures. Okay, so this is very important, the derivation, that is to calculate the packing efficiency in HCP and CCP or FCC. Now next, let's calculate the packing efficiency in BCC, body centered cubic lattice. So the next is packing efficiency in BCC structure. So again I am going to draw a cubic close packed structure. Now BCC, body centered cubic, means we have atoms at the corners and one atom at the body center. Now I am going to name this. This is A, B, C, D, E, F, G, H. Now we have atoms at the corners and one at the body center, and they are touching each other. Okay. Now this body diagonal AF, let it be equal to C, and the face diagonal FD, this is FD, let it be equal to B. And you know the body diagonal C, this is 2R, this is R, and this is R. So again we can say the body diagonal C will be equal to 4R. Now let the edges, all the edges are of length A, and here we are going to take DE, and the next edge as EF, this one. Let this be equal to A. Now we are going to start the derivation. Now we know the BCC has two spheres. We have already discussed it. What is the number of atoms in body centered cubic crystal? It is equal to 2. Now you know the expression for packing efficiency. Packing efficiency is equal to volume occupied by two spheres divided by total volume of unit cell. Now volume occupied by one sphere is 4 by 3 pi r cube. So what will be the volume occupied by two spheres? It will be 2 into 4 by 3 pi r cube. Now we have to find the A, volume occupied by the total volume. Total volume is A cube. So we have to find A, an expression for A first, and then substitute in total volume. So to find A, let's consider the face diagonal, that is DF. And we know face diagonal DF square is equal to EF square plus DE square. Now we know that DF is B. So B square is equal to EF, and DE are the edges. So A square plus A square, or we can say B is equal to root 2A. Now let's take the body diagonal. For that triangle, to consider the body diagonal, we have to take triangle ADF, this triangle ADF. So in triangle ADF, we can say that AF square is equal to AD square plus DF square, or AF is equal to C. So we can write C square is equal to AD is B square, AD is A square plus DF is B square, or we can write b we got as root 2a, or we got b square as 2a square, that is a square plus a square. So I am going to substitute that b square here. So c square will be is equal to a square plus 2a square, or c square is equal to 3a square, or c is equal to root 3a. Now we discussed that c is equal to 4r. C is equal to 4r. So we can write 4r is equal to root 3a, or from this you can write the expression for a is equal to 4r by root 3. So this is the expression to find the edge length of a body centered cubic lattice. What is that expression? A is equal to 4r by root 3. Now you can write for radius also from this expression. R is equal to root 3 by 4a. So this is the expression to find radius. Okay. Now let us substitute. We can find the volume. We got A. So what is the expression to find volume? Volume of cube is equal to a cube, which is equal to 4r by root 3, the whole cube. And let's substitute this in the expression for packing efficiency. What is the expression for packing efficiency? Volume occupied by 2 spheres. Packing efficiency will be equal to, volume occupied by 2 spheres will be 8 by 3 pi r cube, that is 2 into 4 by 3 pi r cube, divided by, we have 4r by root 3 the whole cube, and you get, after solving this, the packing efficiency as equal to 68%, which means that 68% of space is filled by particles in case of body centered cubic lattice. Okay, so this is how we calculate the packing efficiency in BCC. Now next we are going to calculate the packing efficiency of a simple cubic lattice. So 3 is packing efficiency in simple cubic lattice. Now again we have to draw a cube structure. Now simple cubic lattice means the atoms are present only at the corners, and we know the number of atoms in a simple cubic lattice is 1. Now we have atoms at the corner, so I am going to take these 2 corners, I am going to draw atoms, and these atoms touch each other. So you know, if this is R, this is R, which means this is our edge, that is A, edge A, and you can name it as A, B, C, D, E, F, G and H. Now let's derive. For that you have to write the expression for packing efficiency. Packing efficiency percentage is equal to volume of one sphere, because here we have only one atom in simple cubic lattice, divided by volume of unit cell, cubic unit cell, into 100. Now volume of one sphere is 4 by 3 pi r cube. 4 by 3 pi r cube. Now here you have to find A, edge length A. You know, you can see from the diagram that A is equal to 2r. So this expression we have to learn by heart, that is the expression to find the edge length of a simple cubic lattice. The expression is A is equal to 2R. Now you can find the volume of cube. Volume of or unit cell. Volume of unit cell is equal to A cube, which is equal to 2R the whole cube, which is equal to 8R cube. Now you can substitute. You got volume of unit cell and volume of one sphere. Substitute in the expression for packing efficiency. Packing efficiency will be equal to 4 by 3 pi r cube divided by 8r cube, and you get the value as equal to 52.4%. So in simple cubic lattice, the packing efficiency is 52.4%. So when you compare the packing efficiency of HCC, BCC and simple cubic lattice, which packing is more efficient? It is HCP and CCP or FCC. After that comes the percentage packing efficiency percentage in HCP is 74%, and in BCC it is 68%, and last comes simple cubic lattice where its packing efficiency is 52.4%. Now the expressions to find edge length is very important in all the three cases, because when you find the density of solid or density of unit cell, what is the expression to find density of unit cell? Z into M by A cube Na. So if you know the type of, if you are given in the question the type of lattice, you have to find A using the expressions, and we know what is the expression for A, edge length for different packing, the edge length A for simple cubic lattice, the expression for A is equal to 2R. Now for BCC, the expression for A is equal to 4R by root 3, and for FCC or CCP and HCP, the expression for edge length A is equal to 2 root 2R. So this is very, very important, the three expressions which you have to use when you find the density of a unit cell. Okay, from this you can also find the radius. If you know edge length A, you can calculate the radius. So with this we complete our packing efficiency. Thank you.